you had some issues with. We had a few people in this morning getting some help on some things. We're going to learn our new technique today, or our last new technique. So we really have 3 ways of doing these, and we'll talk about that today. So, yeah, sure. 37. 37? What was 37?
Tangent of x to the 4th times secant squared.
Like this? Okay. All right. Did you have an idea, a thought for the U on that one, or is that where you got stuck? Yeah. Anybody have a idea? Sine squared? How'd you come up with that? Where's a sine squared? Tangent is so tangent to the 4th would be like sine to the 4th over cosine to the 4th. Let me think this through. Right? Is that not? You're not as happy with that substitution now. Now that you okay. All right. I was trying to think. I'm not sure where that would get it. If that would get us there. Anybody else? Tangent x. How about if we just let u equal tangent x? Now, why would that be a thought? Because the du is secant squared, which is sitting right there. And so then this would become u to the 4th, right? Because remember, tangent to the 4th is the whole tangent raised to the 4th power. So I think that's a good plan. So if we let that be tangent, this is secant squared x dx. So now my substitution, this part would just be u to the 4th. This part would be just the du. Right? And so the antiderivative is now 1/5 u to the 5th plus c. And then we put in our tangent, we put our tangent back in, so the tangent to the 5th. Like so. So the guiding principle is something on the inside, which certainly tangent is on the inside, but so is secant, is on the inside here. But what would guide us to let u be tangent is that we could do the derivative, get secant squared, and it's sitting right there. What's that? 58. All right, 58 was, help me out. Definite integral.
X times the cube root of 4 plus x squared dx.
4 plus x squared. There's a cube root. So it would be that right there. Right? I mean, as soon as you see a square root or a cube root, you should be writing 1/2 power, because that's all of our derivatives and antiderivatives need to have a power. So right away, you should write it that way. And so what is your thought for your u?
4 plus x squared.
The inside, right, would be a good thought. So 4 plus x squared. So the du would be 2x dx, which I think is going to work out nicely because I can see that I've got an x dx right there. So that just tells me I'll move this 2 over to here. And that's going to be x dx. And so when I sub out the x and the dx for the 1/2 and the du, and then this whole thing is just u to the 1/3. So Anna, this is what I was talking about with the work. Anna, this is what I was talking about with the work. You know, I mean, I would just. It seems like there was a lot there that needed to be there. All right, so we get this. Now here's the next thing. Notice, now I don't care which way you go here, but right here, we haven't subbed those out. Do we need to? Okay, we don't need to, but it's not a bad idea. I mean, one thing you can do is you can go ahead and do your antiderivative, go back to your x's, and then put your 0 and 2 in. But remember, the 0 and the 2 are x values, not u values. So I shouldn't put a 0 and a 2 on this. It would really be wrong. It would be incorrect notation to have a 0 and a 2 here, because that would be mixing up x's and u's. All right, so what I could do, one thing I could do is take these and put them where? In for the x right here. So 2 squared is 4 plus 4 is 8. So this one would turn into an 8. And this 0 put in for x would turn into a 4. And then I would have this. Now I raise that up to 4/3 and divide by 4/3. Well, that'd be times by 3/4. And then I have this half out there, so that makes 3/8. So I have 3/8 u to the 4/3, and then I can put in my 8 and put in my 4. Now, I don't have to. I could do what Brenda said. I could have, let's do that in red over here. I could have then went back to my x's, which was 4 plus x squared. So I could have had 3/8 4 plus x squared to the 4/3 and done that from 0 to 2. So I could have done that. Or I could do this one. They're going to come out the same. So in black, I'll do them both. So both of them are going to end up being the same. They're going to be 3/8. If I put a 2 in here for x, I get 8 in here. If I put an 8 in here for u, I get 8. So I get 8 to the 4/3 minus 3/8 4 to the 4/3. Okay? That is not good enough. Why is that not good enough? What can I simplify? This one. Not so much this one. Now I could do 4 to the 4th, and then I could do a partial cube root, but you don't have to worry about that. But the ones I do want you to simplify, if you get a perfect square or a perfect cube in one of these, and then you should be able to simplify that. So the cube root of 8 is 2. 2 to the 4th is 16. If I take 3/8 times 16, the 8 cancels 16 is 2. That whole thing would just turn into 6. So you need to be able to do that. Now this one, I can't really do anything with, so I'm not going to. I mean, there would be some things I could get into, some partial roots that I could kind of simplify down. But for example, if you get square root of 8, leave it square root of 8. I'm okay with that. You don't have to make it 2 square root of 2. Okay? Now if you get square root of 8 minus square root of 2, then I think you should simplify that. Right? Square root of 8 minus square root of 2 would be 2 square root of 2 minus square root of 2. So you should probably simplify that. But if the answer just came out to be square root of 8, you know, again, if it was something like that that was going to keep you on the borderline for passing or not passing, then I don't know.
But you can't put the 2 and the 0 in for the u.
You can't put the 2 and the 0 in for the u, absolutely not, because those are x's just like these are x's, right? So this is the area from the x value of 0 to the x value of 2. So yes, you cannot put the 0 and the 2 in for the u, absolutely not.
So how'd you get the 4 and the 8?
Here?
Yeah.
Well, it depends. If you go back to the x's, right? You'd put a 2 in here for x, right? So you get 2 squared is 4, 4 plus 4 is 8, so you get an 8. And then you put a 0 in here, 4 plus 0 is 4, and so you get a 4, right? So how did I do it here? I said, well, these are x's. So if these are x's, I can substitute those in for that x and get the equivalent u. So I put them in here, and then I put them on there. So it ends up being... So you notice either way, you end up putting a 2 in here and a 0 in here. Either you do it here and put it on there, or you do it in here when you go back to the x's. I mean, one way or the other, you're going to put it in there. Okay? All right, so that's number 58. Another one. Yes, Logan. 35? What was 35? Okay, just like that. Okay? And anybody have a thought of what I could pick for you? This is an interesting one. You actually have two choices, and they'll both work. You could have let u be the cosine of 2x. But let's say we pick u to be the sine of 2x. Why is that a good choice? What is du? Cosine of 2x, which is sitting right there. So when we pick u to be sine 2x, now it's not quite that. Actually, the derivative of this is 2 cosine 2x dx. So this 2 is kind of in the way, and so we'll move it over there. And we got that. So the integral, when I substitute, this is just u, and this cosine 2x dx is just 1/2 du. So the whole thing just turns into that. So now we're going to raise that up to a 2 and divide by 2. We're going to get 1/4 u squared plus c. So we get 1/4 sine 2x squared plus c. Right? And again, we know that that's the case. We check that if we do the derivative of this. If you do the derivative of this, you remember this is on the outside. This is all squared. So you bring this would be 1/4 sine 2x all squared. This would be a double chain rule. You bring the 2 down in front. That would be 1/2. You leave the sine 2x alone. You kick out the derivative of the inside. What's the derivative of sine 2x? Cosine 2x times the derivative of its inside, 2. The 2's would cancel, and sure enough, when you do the derivative of this, you get right back there. And that's why it's the answer. All right. The one nobody's asked about that I'm curious about is number 24. 1/2 square root of x dx. Do I have to do a u substitution? No. Turn to page 333. One more time, let's turn to page 333 in your book. Now, I said a minute ago that there are 3 different ways that you can do, or not 3 different ways, but as of right now, there are basically 3 kind of techniques that we can do these antiderivatives. Now, one is just a basic antiderivative. Now, when I say basic antiderivative, I'm talking about page 333. Those are the basic antiderivatives we have to be able to do. Power rule, sine, cosine, e to the x, 2 to the x, like is in there. The 1/1 plus x squared, which is arctangent. 1/square root of 1 minus x squared, which is arcsine. 1/x is ln x. We've got to be able to do those basic antiderivatives. Or versions that can be turned into those. And really, that's what all our techniques are, techniques that turn them into those basic antiderivatives. Let me give you a couple of quick examples here before we do number 24. If I gave you this problem here, are you going to do u substitution on that? No. No. What would you do? Split it apart. X over x would be 1. 1/x. So this would just be a power rule for this one, which would just be x. And then this would just be ln x, right? So 2 different basic antiderivatives off of page 333. But sometimes they have to be rewritten. We had some like this the other day. If I gave you this problem, are you going to do u substitution? What are you going to do? You're going to distribute that and then do a power rule, right? So those are the ones that, now you had some of those in the LH packet too, where they gave you, say, an x out here and then an x plus 2 to the, say, the 5th power. Now that one you are going to do a u substitution, right? Because you can't distribute here. So now you do a u substitution on the x plus 5, and then that allows you, when you have an extra x, what do? When you have an extra x, you solve for x and substitute that in, and then it turns it into something like this, where you can then distribute and then just do your basic antiderivative. So understand, basic antiderivatives is something we sometimes see, and that's all this one is. If you noticed, all you had to do is pull that 1/2 out in front, and then this square root of x on the bottom is just x to the negative 1/2, and you didn't have to pull it out in front. I mean, you could have left the 1/2 in there too, but, okay? That's just a simple power rule is all that is. So you raise that up 1, which is a half. You divide by a half, which is times by 2. You times by 2, it'll cancel that. That's just x to the 1/2 plus c is all that is. So remember, keep in mind, we're going to learn another technique today. So one of the things you have to be able to do on the Gabor test is be able to identify, okay, what does this one mean? Is this a U substitution? Is this one I could just rearrange and rewrite, split it apart, whatever? Or is this new thing we'll be learning today? Now, did anybody try U substitution and get it to work? Yeah, there were some people who came to me and had tried U substitution, and that's fine. I mean, Brenna, what'd you use? U equals what? The whole bottom? Melissa, did you do the whole bottom? And I had some people just do the square root of x also. But watch what happens here. If you let u be the bottom, here's where people usually run into trouble when they let u be the bottom. They let u be the bottom, so they've already got it in their head that they're going to do that down there, right? Now you can, I mean, it does work. This is the interesting thing about this one. It's got about 10 different routes you can go that all end up getting you to where you want to be, okay? But one idea when people make this choice is right away they think they're going to do that. Well, let's do the du. So the du would be, what, bring that down, that'd be x to the negative 1/2 dx, which would be the same as 1 over square root of x dx. So if you notice that, that's that right there, isn't it? So actually I should have done that in a different color. So in red, if I would have noticed that, hey, this is just the du, I could have done that right there, and then what am I left with? 1/2. What's the antiderivative of 1/2? 1/2 u plus c. And what did we say u was? U was this. So that'd be 1/2 times 2x to the 1/2 plus c. Sure enough, the 2 and the 1/2 would cancel, and there's your answer, x to the 1/2 plus c. So it worked. Let's finish the one in the blue. If you did it this way, and you said, well, that's u, so that would be this, that'd be this part. And then here we have a 1, and I still have the dx I got to sub out. Well, what would dx be? Dx would be square root of x times du. Now, I told you I don't like to mix up x's and u's, but here might be a case where you'd have to. So if I move my dx over here, dx is square root of x du. So I come in here and I say, well, okay, what's another name for square root of x? Oh, wait a minute. U was 2 square root of x, so what's square root of x? 1/2 u. So square root of x would be 1/2 u. So instead of square root of x here, I can have 1/2 u. So I come over here and I put 1/2 u du. Well, sure enough, the u's cancel. And then we end up with a half, and then we do the antiderivative, which is 1/2 u, and then boom, you're back to the same thing. So it sure is a lot of work for something that should have been a lot easier than that, right? But like I keep using the analogy of a fork in the road, but I mean, that's what you get. I mean, sometimes this way is a shortcut, but you don't know. You start down the long road. Well, you'll get there eventually sometime. Okay, sometimes you'll get to a dead end, and you'll have to turn around, and you'll have to come back. And it just happens, okay? Hopefully, here's the thing. Hopefully, Bailey, if you take my suggestion of doing those extra book problems, you'll more likely be able to see which fork in the road to take. Now, I say that, I'm kind of kidding, because really, I'm going to assign these problems to you, and I'm going to check because I think they're the minimum you have to do. Now, I know on my assignment sheets, I always put at the top, I don't know if you notice that, but at the top of my assignment sheets, I say these are the minimum to do. Well, in this case, I really mean it. Like if I say do 5 or 10 out of the book, that should be a minimum. I mean, I'm just thinking, hey, to pass this gateway, I think you need that. Now, you might feel really good about where you're at with these and think you don't need that much practice. That's fine. And you'll probably pass it the first go-round. But it's, it is something, how much you want to do. I'm going to give you some websites you can go to. We're going to do some in-class practice, but for some of you, the in-class stuff may end up being enough to get a pass. All right, any in the book. Let's see if you did some in the book that you were stuck on or something just didn't seemed like it was something new you hadn't seen before. Spencer. Yeah. Anybody else, Cody?
37.
What's 37 say?
Definitely will x squared over 1 plus x plus 6.
Okay, number 37. Okay, anybody have an idea on this one? X cubed. There's two reasons that that will be a good idea. One reason is, of course, the du, right? The du is going to give us 3x squared dx, and there's an x squared dx setting right there. So that's certainly why we would want to pick that. But the other good reason is, then what do you get down here? 1 plus u squared is what? Arctangent, right? That's something you just got to be able to recognize. That's on page 333. That if you can get a 1 plus u squared on the bottom, that's oftentimes an arctangent. So that is going to be a good one to pick. We did one similar to this the other day where it was number 11, remember? And they let u equal x squared, and we were like, how in the world did they come up with that? Well, now we saw what happened. It ended up giving us an arctangent. Okay, so the 3's kind of in the way, so we'll move that over. And so our x squared dx will be replaced with a 1/3 du. The bottom is going to be a 1 plus u squared, because x cubed squared makes x to the 6th. And that is just a nice arctangent antiderivative. Arctangent of u. And put the u back here. Okay, so it's that recognition thing. Yeah. Cool. I think that is one I wanted to do today. Is that the one with the x plus 4 on top? Yes. Good. Now, if you haven't had a chance to look at this one, just let's let everybody take a second to give a thought to what they would pick for a u there. Just the x squared? Problem with that is you'd have a 1 plus u on the bottom. What else would be an option for you? I think the whole bottom is that's the one I would think of first. The whole bottom. Let u be 1 plus x squared. But what's the problem? I mean, what do you run into if you let u be the bottom? Okay, so if I let u equal 1 plus x squared, the du is 2x dx. Now I can divide the 2 over, right? So I've got an x dx. So I mean, again, my question is, so what's the roadblock here? What's the problem? The plus 4, isn't it? I mean, really, if the plus 4 wasn't there, we'd be in great shape right now. Keep. Well, now wait a minute. You said something interesting there about separating. but I can't, I mean, there's no way to get a plus in here. I mean, I can't like add a 4 here, for instance. Logan?
You separate it so it's x over 1 plus x squared.
That is the key. See, and when you said separate it, yeah, see, I remember we can never separate a bottom, but we can separate the top, right? And what we're seeing here is we'd love to have an x dx. Well, we can get an x dx because we can separate this problem into, and that's exactly what you have to do on this one. Now we've learned, and this is where all this extra practice I keep talking about comes into, because we've got all those problems in the book on page 340, and there's a lot of different ones in there that have different little quirks to them or something comes up, which you don't really know about until you've tried a bunch of them. And so, like this one ends up being x over 1 plus x squared dx plus 4 over 1 plus x squared, then dx. Right? That is perfectly legal. You can't split the bottom, but you can split the top. You just got to keep the bottom together. So now what? Now it's just 2 problems. Yeah. So this first one we'd go. Yeah. So go ahead and do it. I'll give you a little time here. Go ahead and finish it then. All right, did you get something? Isn't that second one just an arctangent then? Something like that? The first one, because and so it's kind of an interesting problem because it points out just very subtle changes in the problem make it a different attack. On this one, because we have the x on top, we wanted to let u be the 1 plus x squared. It gives you the x dx. But on the other one, where you have a 4, it's like you can just pull that 4 out in front. And it's just an arctangent. So it's just 4 arctangent. Okay, questions about that one? All right. Probably better call it good with that. And let me, once you get your notes out, let me show you the new thing that we have to deal with today. All right, so the one that we're going to try to deal with now is going to be a problem that looks like this. The integral of x times e to the x dx. I think I put one like this up here the other day. What is, I mean, you think about it, can you do something like page 333? Well, no, you can't split this apart because of the multiplication. I mean, if this was plus, yeah, we could do their individual antiderivatives, but we can't do the antiderivative this, then the antiderivative that. That doesn't work. So then the only other thing we know about is, well, we could, is there any way to rearrange it? Well, no, you can't really do anything to it. It's just very simple. It's just two little functions there. Is there a u substitution that would work? I mean, since you don't know anything else, you might try a u substitution here. Now, keep in mind, what all these techniques really are just a way of these techniques, and this new one we're going to learn is just a way to take the integral you don't know how to do and turn it into an antiderivative you do know how to do, like one on page 333. That's the whole point of these techniques. So since all you know right now is u substitution, let's pretend that we weren't going to learn a new one and we thought we could do something with u substitution. So what would you think to try? About the only thing could be is e to the x, because we said you can't let u be x. So that's about the only option you got. So let's try. And so the du would be, which is kind of nice. It's sitting right there, right? So this integral, I could take this piece out and replace it with just plain old du, right? So e to the x dx I can take out and replace with du. Now I got an extra x sitting there. Oh, we know how to handle that. How do you handle an extra x sitting there? Solve for x, right? So let's take this and let's solve for x. How do you, natural log. So that'd be natural log of u equals x. So I can replace that with natural log of u. Now the whole point of doing the u substitution was to turn it into an integral we know how to do. Do we know how to do the antiderivative of natural log? Now, we don't. However, there's no reason it couldn't have been on the list on page 333. It's just we decided, the book authors decided, we're just going to make you memorize these. We could have added some more onto there. It's not that hard a one. You can do this on your calculator. Okay? On the calculator, if you do natural log of u, du, I think it comes out to be, well, I can't remember. I think it's u ln u minus u. I think. Is that right? And I think that's what the antiderivative of natural log is, but that's one we've chosen not to memorize. So it turns out we could have done a u substitution, but it turns it into an integral we don't really know how to solve. Sometimes that happens. So we're going to have another technique. Now, it doesn't always work. It doesn't always happen that you have two different techniques that'll work on the same problem. This happens to be one where they both will work. Most of the time, not. Okay, now, I'm not done with this. I'd have to put my e to the x back in, and this would end up being this. And what's another name for ln e to the x? Just plain x. So this would really be x e to the x minus e to the x plus c is actually what we would end up with here. Okay, and if you type that into your calculator, now you'd have to remember to put a time sign in between them. I think that is what you get. Okay, well, we're going to learn a new technique today that's going to deal with this. It's the product rule. Now, that even looks like a product, but it's not just because it looks like a product, because we've done a lot that look like products. Matter of fact, this right here looked like a product, and we didn't do this new technique on it. U substitution worked just fine. Okay, and here's another one that was a product, but we didn't use this product thing. So just because it looks like a product doesn't mean it's going to be this new technique. But it is the reverse of the product rule. So in your notes, matter of fact, I would recommend you not even put this in your notes, to be honest with you. If you want to, you can. But I'm going to write down the product rule. once we get the final result, we're definitely going to want to write that down and memorize that. But here's the old product rule right here. Oops, U prime V, U V prime. Okay, so there's the old product rule. And since this new thing we're going to have is going to be the reverse of the product rule, well, that's what we want to do right now. We want to undo or do the reverse of the product rule. So what we're going to do, since this says do the derivative with respect to x, remember u and v are just functions of x. What I'm going to do is do the antiderivative of both sides with respect to x. So I'm going to do the integral dx of this side and the integral dx of this side. Okay, I'm doing the antiderivative of both sides. Now, what do I get on this left side? What would you get on the left side? No. What do I get here? This is a derivative of uv, and I do the antiderivative of it. So I just get uv, right? They're just going to cancel each other out, right? I just get uv. Okay, antiderivative of the derivative. Now, plus c, we don't have to worry about a plus c on there because that'll take care of itself at the end. We'd have c's on both sides, and so we can just put the constant on at the end. Okay, now this I'm going to split into two different integrals. So I'm going to split this into the integral. So I'll split this into two, both with the dx here, and I'm going to write u prime. What's another way to write u prime? What's another way to write u prime? du over dx, okay? So u prime, I'm going to write du over dx times v and then dx, right? And because I'm splitting this into two different integrals, both with respect to x, okay? So then this will be the integral of u, and then instead of v prime, I'm going to put dv over dx, and then with respect to x, okay? So this is going into both parts of it. So I've just split that up that way. Now, what do you notice happens here? The dx would go away. And so that would go away, and then the du I'll write on the other side of that. So I get the integral of v du. And then on this one, the dx goes away, and I get the integral of u dv. Okay? And then the last thing I'm going to do is I'm going to subtract this integral over to this side. So I've got uv minus the integral of v du equals the integral of u dv. Okay? And that is what we're going to write down. You'll see here in a second. The reason I subtracted there is because think about what substitution does. It allows us to take one integral and replace it with a new integral that hopefully we'll be able to do. So that's what we're going to do in this new thing that we're doing now. Is this side's going to represent our original integral, and then we're going to replace it with this side. And the hope is that this integral will be easier to do. Okay? So, here's what you're going to write, what you should write in your notes. This is called integration by parts. Integration by parts. Okay? Not really sure why it's called that, or where the name came from. That's what we're going to call it. All right, and so I'm going to write down that little formula I just had there, which was this. Integral of u dv is equal to uv minus the integral of v du. You've got to pretty much have that memorized. Okay? You pretty much have to have that memorized right there. Integral of u dv is equal to uv minus the integral of v du. So, the goal for us then is to, so let's take that problem that I had written up there a minute ago, which is the integral of x times e to the x. dx. Right? We tried u substitution. It gave us an integral we didn't know. So, I mean, if we would have known natural log, but a lot of these will give you an integral. If you tried u substitution, it wouldn't work. Most times it just wouldn't work. And it's not a basic antiderivative that we can deal with. All right, so what we're going to try to do is make it match this. Now, what we're trying to do is this. This side is our original. So the left side here is our original integral that we're starting with. Now, it's made up of two parts. Maybe that's why it's called integration by part. It's made up of the u and the dv. So what we need to do is figure out which part do we want to be the u and which part do we want to be the dv. And we're going to write it like this. Just like we've done with our u substitution. Underneath here I'm going to put u, what u is, and then over here I'm going to put what dv is. Now how do we decide what to pick for u and what to pick for dv? Well, how we pick is based on what we're going to do with it. What do you suspect we're going to do with what we pick for u? We're going to do the derivative to get the du, because we got to put that in over here. So we want to pick something for u that we can easily do the derivative of. What do you suppose whatever we use for the dv, we're going to do with that? We want to get v. We're going to do the antiderivative. So we need to get something that we can do the antiderivative of. Now, we're much better doing derivatives than we are antiderivatives. The ones we can do the antiderivative of is a pretty small list. Okay, now in this problem, you might say, well, if you let u be the x, what's the derivative? 1. What if you had it be the dv? What's the antiderivative? 1 of x squared. Which would you rather have? Well, you'd rather have 1, wouldn't you? So it might be good let that be the u, because then the rest of this would be the dv. And what's the antiderivative? E to the x. Oh, that's really nice, right? E to the x is easy to do the derivative of, but it's really easy also to do the antiderivative. So that's your thought process. Well, if we think about that hard enough, and people already have, luckily for you guys, is we can have a nice little acronym that can help us decide what we should pick for our u, and therefore the rest be the dv. But again, the guiding principle is this. The thing you pick for the u is something that's easy to do the derivative of, but more importantly than that, the thing you pick for the u is something you don't want to have to do the antiderivative of. That's the real key reason. Okay? So here is what we're going to write. It's Italian. Liate. No, it's not. It's just an It's not Italian. It's just an That's how I pronounce it. Liate. Yeah. Liate. So what this is the order that we would pick functions to be u. Now remember, what we pick for u are things we don't want to have to do the antiderivative of. So the first one in the list is logs. As we just learned a minute ago, we don't know the antiderivative of ln x. I mean, we do now, we just wrote it down, we just did it on the calculator, but we're not going to memorize it. So if you have an ln x in there, we can do the derivative easily of ln x, but we can't do the antiderivative. So we do not want that to be our dv. So we better have it be the u. Okay, the next one is the I, and that stands for inverse trig. This would be like your arc sine and your arc cosine. We can do the derivative of arc tangent, 1 over 1 plus x squared. The derivative of arc sine is 1 over square root of 1 minus x squared. But we don't know the antiderivative of arc tangent. That's not in our list. We've never done it. So logs and inverse trig, we do not want to do the dv with those. So we're going to pick those first as our u's. Okay, the A stands for algebra. This would be like your x squared, your x cubed, those kind of things. Now, like we just saw, we can do kind of both. X is a nice one to do the derivative. It's 1. The antiderivative is a little more complex, 1/2 x squared, but we can kind of do either, so it's kind of in the middle. All right? And then the last ones you're going to pick for your u are going to be your trig and your exponentials, like your e to the x. Because like we just saw, e to the x is a great one to have for the dv. Sine and cosine are nice ones to have for the dv because you can do the antiderivative of those. So those are great ones to have for the DV. So those are your last choice you want to pick for the U. All right. So there you go, Liate. This tells you what you pick for your U, and the rest will be the DV. So in this option here, what are we going to pick for the U? What do we have? We have algebra, and we have an exponential. So we'll pick the algebra as our U. So we're going to let U equal X. So there we go. Remember I said we never let U equal X? Well, on U substitution we don't, but on this we sometimes do. So we're going to let U equal X, and the dV is everything else. E to the X and the dx. Everything has to be accounted for, just like in U substitution. So you pick something for the U, everything else has to go into the dV. All right, so below the U we're going to write what? du. Okay, what's a du on that? 1 dx. So we'll just put dx. We don't need the 1. And what are we going to put under the dv? V, the antiderivative. And what's the antiderivative of e to the x? E to the x. And we remember the dx just goes away, just like it always has when we do the antiderivative. That just means with respect to x. Okay, now what we do is we plug into this formula. Okay, so what this is saying is here's our original integral with the u's and the dv's in there. So this has got to be equal to this. So we write u times v, so there it is. U times v would be x e to the x minus the integral of v, which is e to the x, and then du, and du is just dx. And did we accomplish what we wanted? Did we get a new integral that is easy to do? Absolutely. So we got x e to the x. This antiderivative here is just e to the x plus c, and I think that even matches what we got on the other page, doesn't it? Right here.
That's right.
X e to the x minus e to the x. There it is right there. Okay? This stuff's so exciting, it's got Spencer all choked up. All right. You guys try this one. Yep. 3x sine 4x. You guys try that one. Yeah, we give you a few minutes here to get the U, the dV, the du, the v. Get all 4 of those pieces written down. Double check with each other if you want. I'm going to put that up here. Just so you don't go too far down the dead end road. Okay, just at least make sure you've got that part right. All right, how are we doing now? We got algebra in there and we got trig. So according to Liate, we'll let you be the what? The 3x, right? Okay, I'm gonna put it up here, what all four of those should look like. Okay, did you remember about the 1/4? Okay, because you got a 4 in there, when you do the antiderivative, you're kicking out a 1/4 because of that 4 in this. Remember, that's antiderivative. So here you're doing derivative, over here you're doing antiderivative. You gotta keep those straight. Now, another thing I want to caution you about as you go forward now and use the formula. You never, with this 3 here, like you have 3 dx right here, we never move that over here like we do in u substitution. We never take this 3 and swing it over here as a 1/3. We're so used to doing that sometimes I'll see people when they're doing integration by parts, they'll start moving stuff around here. We don't do that. Because all we're doing is we're taking the u and the dv and the du and the v and we're plugging them into that formula. So we don't want to move any stuff around here. All right, so go ahead and take those and plug them into the formula and see what you come up with. Okay, here's the first step. Now, when you get one like this, there's parts of it you can do in your head, and you don't have to write down every little bit. But yet, you got to be careful you don't lose a negative or you don't lose a fraction or something like that. But I just wrote it. So now I'm not done here yet. But I just wrote it so it matched the formula. The formula is u times v. Well, I guess I did kind of combine there. I took the 3 and the negative 1/4 wrote negative 3/4. It's in there. Right here.
Yes.
All right. My bad. All right. Yes, I forgot the X. I know. See, I can't. I get this because I'm not being graded. So I can mess up
He
everything.
gets paid the same.
I get paid the same. You don't get ones on the AP. All right. So yes, it is an X. Thank you. And then v du. So that'll make a negative 3/4, which can combine with that negative to make a plus. Okay, I suppose I'm missing my X everywhere now. Yeah. Oh yeah, there it is. And so, there we go. And so that turns into a plus 3/4. And then don't forget when I do the antiderivative of that new integral, because that's what I have is a new integral that's an easy one to do. And when I do the antiderivative of that one, I'm going to kick out another 1/4. So that 3/4 that was set in there ends up being a 3/16. Okay? And then that is what we're looking for. So remember, we did say sometimes the integral is messier than the answer with these because it's a reverse derivative, but that's not always the case, especially on these, because what would happen is if you did a derivative on this, some things would kind of combine and cancel and so forth. But But that is called integration by parts. Now there's a couple, well, there's 2 or 3 things that can happen that are kind of strange on integration by parts. One is you get kind of almost a cycling kind of thing like we did with Newton's method, kind of a never-ending loop kind of a thing. We're not going to mess with that one. There's another one that I think shows up in your homework where you do a well, it can work either way. You can do a U substitution. Now remember, all these techniques are giving us a new integral that we can then do, hopefully do. Well, sometimes you'll do an integration by parts, and then the new integral you get needs a U substitution. Well, actually, this is a case of that, because we can technically do a U substitution right here on this 4x, right? So sometimes you do integration by parts, and the new integral needs a U substitution to finish it out. And it works the other way too, where sometimes you do a U substitution and that gives you a new integral that needs integration by parts to finish out. Okay? So that, I think, may happen on one of the homework problems. And then there's one other thing. Let me show you this situation. We're not going to finish it, but I'm going to have you start. Okay? X squared e to the x. So let's just walk through the beginning of this. We let u be what? X squared. Not because it comes first, but because it's the algebra. We got algebra and an exponential. According to Riate, algebra would come first. So the dv would be e to the x dx. Now the du would be 2x dx, and the v would be e to the x. So now we do our integration by parts formula, and we get u times v, which would be x squared e to the x, minus the integral of v du. So that would be 2x e to the x dx. You have to do it again. Because look what happened. Your x, we did make progress. The x squared is now an x to the first. It now looks like this one here that we did. So what would happen here is you would now do an integration by parts on just this piece. You have to do it twice. Now what if this was x to the fifth? 4 times? You're not going to have to do it 4 times. But you might have to do it twice. You might have one you have to do twice. So you would plug into your integration by parts formula, you'd get to here, and you'd say, oh, that's going to need integration by parts again. So you would do integration by parts just on this, but you would have to not forget about this. This would have to come along as part of your final answer. This stuff over here. And the minus would have to distribute through. So you'd have to be careful with that too. Okay, so if you want to finish that as part of your homework, it wouldn't be a bad thought. But that's the some of the things that can happen with integration by parts. Let me give you one last comment about this, and I'll show you what the homework is. So how do you identify these? Okay? Not just the fact that there's a product there, but another thing that you notice in all these is there's a mixture of the different function families. Like this had algebra and trig together. If you go back to our original problems we've done, that's like all algebra in that one. Here's all algebra in that one. Here's pretty much all trig. Here's all algebra. Here's all trig. If you notice in a lot of the U substitutions, they're kind of the basic families of functions are kind of all within one problem. There's not really a mixture of them. Now, there could be, I mean, for example, hopefully we would recognize this. Let me just change this a little bit. Let me change this to that. Now what would you do on this one? This would be a great U substitution problem. Right? We would let u be the x cubed. Derivative is 3x squared dx, which the x squared dx is sitting right there. And this would be a nice U substitution problem, not an integration by parts. So it's when there's nothing in the inside that we can do a U substitution with that we might think to then do integration by parts. Okay? All right. So your homework is going to be right here. There's 3 different LH pages. And the reason is that my old book the way the old book worked, the LH book, was it broke up the chapters by function family. So like page 310, you'll notice is all algebra type integrals. And I think 341 is trig maybe. And then I think 356 is like exponentials and logs. So we do a bunch of work with algebra equations, then we go to the next chapter and do a bunch of work with, do the same work but with trig functions and then whatever. So these problems are all just pretty much U substitution. So what is that, about 7 of them? But I would suggest going back to the book, that page 340, and maybe grabbing a few more of those U substitution problems to do as well for practice. And then here are some integration by parts questions. And now notice that jumps clear to chapter 8 in our book. For some reason our book, it is kind of a Calc 2 topic, but I'm not quite sure why. So it's split up. So we have to jump clear to chapter 8 to get the integration by parts stuff.
Did we do that?
I don't think so.